I am Andos Krias. I am working as Assistant Professor in Jyoti Engineering College. Today, I am going to take note topic in design of machine elements. Thin-walled cylindrical pressure vessels. Pressure vessels have many applications in industries. Mainly, cylindrical and spherical pressure vessels are used in industries. It is used as boilers and it is also used as storage tanks. Here we are going to deal with cylindrical pressure vessels. In cylindrical pressure vessels are mainly classified as thick cylinder and thin cylinders. Next we are going to look how a cylindrical pressure vessel is classified as thick and thin-walled cylinders. Thick and thin-walled sections are classified based on ratio of inner radius to wall thickness. If the ratio of inner radius to wall thickness is 10 or more, then that pressure vessel is a thin-walled pressure vessels. That means for a thin-walled pressure vessels, ratio of Ri to T is greater than 10. Ri is internal radius and T is equal to thickness of the wall. For thick-walled sections, ratio of Ri by T is less than 10. For a thin-walled sections, stress distribution throughout the wall thickness is constant because thickness of wall is very thin. But when we consider thick wall sections, for a thick stress distribution along the length of the wall for thick walled section is not constant. It is varying throughout the wall thickness. Now, main applications of thin-walled sections are pressure pipes, aircraft fuselages, and compressed gas containers. Then stresses. Next we are going to look at stresses developed in thin-walled sections. Mainly stresses are developed in a thin-walled section is due to pressure of fluid inside the cylinder. Due to this internal pressure, mainly three types of stresses are developed. These three types of stresses are induced on three mutually perpendicular directions. The types of stresses developed due to the internal pressure are longitudinal stress, hoop stress, and radial stress. Now we are going to look at detail about these stresses. First one, radial stresses. Radial stress developed only due to the internal pressure of fluid inside the cylinder. It is mainly compressive in nature. The magnitude of radial stress is equal to fluid pressure inside the wall and it is zero on the outside the wall if outside section is open to the atmosphere. Due to the geometry of thin-walled sections, radial stress is very small compared to the hoop stress and longitudinal stress. Therefore, usually radial stress are neglected in analysis of the thin-walled sections. Next we consider longitudinal stress. Longitudinal stress is acting along the length of the cylinder. It is mainly tensile in nature and it also tends to increase the length of the cylinder. Next, we are going to find the magnitude of longitudinal stress. To find magnitude of longitudinal stress, we apply equilibrium force equation. We apply equilibrium force equation in x direction. That means sum of all force acting in x direction is equal to 0. Forces developed in x direction is due to mainly two factors. First one, stresses in x direction sigma 2 and fluid pressure in x direction P. The forces are found out by stress into area. Stress sigma 2 acting on stress sigma 2 into 2 pi RT and pressure P into pi R square. That means sigma Fs is equal to 0. That means sigma 2 into 2 pi RT minus P into pi R square is equal to 0. Simplifying this equation, we get sigma 2 is equal to PR into 2T. Therefore, longitudinal stress sigma 2 is equal to PR by 2T. Next, we consider hoop stress or circumferential stress. It is directed along the tangent to the circumference and tensile in nature, and it tends to increase the diameter of the cylinder. To find the magnitude of circumferential stress, we apply force equilibrium in Z direction. From force developed in Z direction is due to stresses acting on Z direction and fluid pressure along Z direction. Stress acting on area 2T into delta x and pressure act on area 2R into delta x. Therefore, sigma Fs equal to 0. That means sigma 1 into 2T delta x minus P into 2R delta x equal to 0. That means stress sigma 1 is equal to PR 2T. Therefore, circumferential or hoop stress is equal to PR by 2T. From the above equation, we can also find that longitudinal stress is always equal to 2 times of hoop stress. These are the main topics in thin-walled sections. Thank you all for listening to this section.